Okay, so for solutions, the two big formulas that you want to remember are concentration of the solution times the volume of the solution is going to be the amount of solute. So I'm going to put solution, solution, and solute. So this can be written much more simply as C times V equals amount. And amount is specifically vague because it depends on the concentration. And the other important formula to use is C1V1 is equal to C2V2. And this is the dilution formula. So this is when you take something of a certain concentration, you add solvent, and you get a different concentration. So C1 refers to the first concentration, C2 to the second concentration, V1 to the first volume, and V2 to the second volume. But these are the two big formulas. And the two big concentrations we use are molarity and probably weight to volume percent. So this is the abbreviation for weight to volume percent, and the abbreviation for molarity is uppercase M. And if we take a look at those two volume concentrations, molarity, let's say you have a 0.50 molar NaCl solution. You'll notice you don't usually write the word solution here, although you could. NaCl is the solute. So what this means is 0.50 moles of NaCl per 1 liter of solution, but I'm going to put NaCl instead of solution. So when you see a volume in front of something like this, that volume refers to the solution. So I have been taken to doing this lately just to be a little more clear. And if you have a 0.50 W/V percent sodium chloride solution, this means 0.50 grams of sodium chloride per 100 milliliters of sodium chloride solution. So, of course, the reason that it's per 100 is because it's percentage, and percentage means per 100. So the idea here is that this is an amount, and this is a volume. And here, this is an amount, and this is a volume. So we can go back to that formula, CV equals amount. If your concentration is molarity, your amount will be moles. And if your concentration is a weight to volume percent, your amount will be grams. So that's the explanation for the generalness of the formula where it says C times V equals amount. Amount depends on your type of concentration. Okay?
Okay.
All right. So let's take a look at some of these problems here. So what is the mass of solute in grams in 125 milliliters of 1.023 times 10 to the negative third molar solution of Na3PO4? So they want the mass in grams, and we could do a C times V equals amount. But we could also do a conversion factor thing. So we know that we have 125 milliliters of sodium phosphate solution. That's given. We know that the concentration is 1.023 times 10 to the minus 3 molar. So rather than write it this way, I'm going to write 1.023 times 10 to the minus 3 moles of sodium phosphate is equal to 1 liter of sodium phosphate solution. So that's moles per liter. And the reason I'm writing it this way instead of as a ratio is because if I write it this way, I'll be comfortable using either side on top or the bottom, depending on what I need.
Yeah.
So I think that I can convert between moles and liters of solution here. And here I have milliliters of solution. So I'm going to take my 125 milliliters of sodium phosphate solution, and I'm going to convert that into liters of solution. And here I'm going to leave the sodium phosphate off. And then I'm going to use this to convert to moles of sodium phosphate. And because they want grams, I'm going to turn that into grams of sodium phosphate. Does all that seem reasonable to do?
Yeah.
Okay, so let's start. 125 milliliters of sodium phosphate solution times 1 liter of sodium phosphate solution per 1,000 milliliters of sodium phosphate solution. So that's the first conversion. The second conversion, we use the concentration. So I'm going to put 1 liter of sodium phosphate solution on the bottom and 1.023 times 10 to the minus 3 moles of sodium phosphate on top. And then lastly, I need the molar mass of sodium phosphate, and I'm just going to Google it.
Okay. I'm running out of room.
Part of the reason is I'm writing solution after everything.
Yeah, I stopped.
So I get 163.94 grams of sodium phosphate per 1 mole of sodium phosphate. So this is going to be equal to, and just to double check this molar mass, I know that sodiums are 23, so that's 69. I know that 4 oxygens is 64. And a phosphorus is probably like 31-ish. So when I add these all up together, I get 4, carry the 1. 6 and 6 and 4 is going to be 16. And so that seems pretty darn close to what I should get, right?
Yeah.
Okay. So when I multiply these numbers out, how do I want to do this? Well, I'm going to pretend that 1,000 will go into that 0.125 times. So 0.125 is like a tenth, but it's not a tenth, right?
Yeah.
1/10 of that is going to be 16, but 0.125 is more than a tenth. So I'm going to say that's not 16. I'm going to call it 20. So now I have 20 times 1.023, which is 20. So I should get 20 times 10 to the minus 3, which is the same as a 0.02-ish.
Okay. That's what I got.
Okay, so how many zig figs do we get?
4.
3.
We don't count the 1.023.
Well, we do, but when we're doing this multiplication, what's the rule for significant figures when you're done with multiplication?
Use the least amount.
The least. Okay, so what do you get? 0.02 what?
1.
0.0210. That's only 2 zig figs.
Okay.
I thought you, the reason I'm asking is I think you did this on your calculator, right?
Yeah.
What does it say? 0.021?
It says 0.02096. So
Okay, so
we're rounding.
0.02096. The 6 makes the 9 turn into 10. And that's what the 10 looks like. You have to count that 0. So here we have 1 significant figure, 2 significant figures, and 3 significant figures. So here, this is one of those ones where leading zeros don't count ever. Trailing zeros do count if there is a decimal. And I definitely see a decimal.
Yeah.
So there's your answer. And this is the kind of work I would expect to see for a problem like this. Now it asks, what is the molar concentration of sodium ions and phosphate ions in here? Well, we have to know that 1 mole of sodium phosphate is equal to 3 moles of sodium ions and 1 mole of phosphate ion. Now, I'm not saying that this is really equal to it, but what I'm saying is that in this 1 mole of sodium phosphate, there are 3 moles of sodium ions, and there are 1 mole of phosphate ion. So if we take this concentration here of 1.023 times 10 to the minus 3 moles of sodium phosphate per how much?
1 liter.
1 liter.
Sodium.
1 liter exactly. So if we take this and we use the 3 moles of sodium, you can see that we're going to get 3.069 times 10 to the minus 3 moles of sodium per 1 liter of sodium phosphate solution. And a much simpler way to write this is 3.069 times 10 to the minus 3 molar sodium ion.
Right.
So now that we know that it's really easy to do this, you can actually do this. Because the concentration of sodium ion is 3 times larger than the concentration of sodium phosphate. So where does that 3 come from? 3 sodium ions. And what would it be for the phosphate?
1 molar phosphate over 1 molar sodium phosphate.
Right. And so this is just an easier way to do the above without doing all that work, but still understanding that the concentration of the ion is 3 times greater here, and it's the same.
Yeah.
Oops. Do you see the mistake I made here? Do you see that mistake? These cancel, so I'm left with sodium ion, and here, this should be phosphate ion. So what was your question again?
Oh, either way is acceptable.
Yeah.
Yeah. Okay.
Okay, so that's that problem. Now here we have what volume of 2.06 molar KMNO4 in liters contains 322 grams of solute. So what we're going to do here is we're going to write 2.06 moles of potassium permanganate is equal to 1 liter of potassium permanganate solution. Or you could write it as a ratio. It's up to you, whatever you like. The important thing is to get rid of that M and write it down as moles and liters, okay?
Okay.
We got an additional person. Hey, Issa, I didn't see you there. Were you there waiting long?
No, no, I just hopped in right now.
Okay.
But
Well,
I just had a question for you at the end.
oh, okay. At the end?
Well, I don't want to interrupt whatever you're doing.
Okay. So what we have here is 2.06 moles of potassium permanganate is 1 liter of solution. That's what this means. We want to know what volume contains 322 grams of solute, and they're talking about the KMNO4. So we're going to start with 322 grams of KMNO4, which is also called potassium permanganate. We're going to convert that to moles of potassium permanganate. And then we can convert that into liters of potassium permanganate solution. So to do this, we need the molar mass of potassium permanganate. And I'm just going to Google it. KMnO4 molar mass. And I get 158.03. So we're going to go with 322 grams of KMnO4 times 158.03 grams of KMnO4. And this goes on the bottom so that the grams cancel out. And we put 1 mole of KMnO4 on top. And then here, we're going to use this one next. And because I want to cancel KMnO4 moles, I'm going to put 2.06 moles of KMnO4 on the bottom. I'm going to put 1 liter of KMnO4 solution on top. Now, this kind of shows you why I write this way. Normally, when you write the molarity, you write 2.06 moles of KMnO4 per 1 liter of KMnO4 solution. So that's the way you normally write molarity. Now, if you take a look at how I'm actually using this, I'm not using this the way it's written. I'm using it upside down, so to speak. And so here, when I have it written this way, I'm very comfortable saying, oh, I want to cancel moles, so I'm going to put that on the bottom. Here, I am comfortable with saying, well, I'm just going to use that upside down. But students tend to have something written and want to use it that way. And that slows you down. Okay, so when we estimate this answer, I think it's clear that 158 goes into 322 almost 2 times, maybe even more than 2 times. And that divided by 2.06 should be around 1. So our answer should be very close to 1.
Yeah, it is.
Not according to my calculator, it's 384.96, which makes me glad that I estimated, because I know I did something wrong with my calculator, right?
Yeah. Or I did. I don't know.
No, my estimate's pretty darn good.
Yeah.
And 0.989 is what I get.
Me too.
And that's liters of KMNO4 solution. So this is the kind of work I would expect to see for something like that.
Okay.
see. Any questions on that one?
No.
Okay, we're going to move along. Identify the ions that exist in each aqueous solution. So here, they're just simply asking us to look at the formula and take it apart for all practical purposes. So I'm going to write the answer next to each one of these. So for A, the ions are in solution are barium ion. And I'm going to go ahead and put how many of them are in solution. So there's one barium ion for 2 chloride ions. And for B, there's one copper ion and one sulfate ion. I memorized the charge on sulfate as -2. And because there's one of each of these, the charge on the copper has to be +2. For C, we have 2 potassium ions. And since those are the cations, I know that the rest is an anion. And I know there's only one of those anions, because if there were more, there'd be a parentheses around it, but there's not. So there's one of these chaps, and there's 2 of these. To have a neutral formula, this has to have a charge of -2. And those are the ions that exist in each of these solutions. Now, it says specify the concentration of each ion. So I'm going to do a little more work down here for A. To get the concentration of the barium ion, I just showed you a little shortcut. We can take the 0.12 molar barium chloride. And since the concentration of the barium is the same as the concentration of the barium chloride, we could put 1 molar barium per 1 molar barium chloride. And therefore we get 0.12 molar barium ion. Now, how does this differ for the chloride? Well, you'd say 0.12 molar barium chloride. But because there's 2 of those ions for 1 formula unit, you'd say 2 molar chloride, 1 molar barium chloride. And your concentration would be 0.24 molar chloride. So I'm not going to show you how to do B and C. It's the same process to get the molarity. Now you can do this the longer way, and that's this. The 0.12 molar barium chloride means 0.12 moles of barium chloride per 1 liter of barium chloride solution. And we know that there are 2 moles of barium, or I'm going to do 2 moles of chloride ion per 1 mole of barium chloride. And what we would end up with here is 0.24 moles of chloride per 1 liter of barium chloride solution. Another way to write this would be 0.24 molar chloride. So you can see these answers that we get are the same either way. This really shows you what's happening with the solute, and this is more of an abbreviated way of doing it. Okay, any questions about this one?
No.
Okay, I'm going to move on. Okay, what mass of oxalic acid is required to prepare 250 milliliters of solution that has a concentration of 0.15 molar H2C2O4? So that is 0.15 moles of H2C2O4 per 1 liter of H2C2O4 solution. So here I've written it the normal way of writing molarity instead of writing it being equal. We want to prepare 250 milliliters of H2C2O4 solution. And here, this is in moles per liter, so that makes me think I want to take that milliliters and turn that into liters. And then from that, I can turn that into moles. And then from that, I can turn that into grams using the molar mass of this stuff. The molar mass of this stuff is 2.02 plus 24.02 plus 64.00, which comes out to 90.04. Okay, so here's how it all looks out, 250 point. Now notice the decimal means that that zero is significant.
Mhm.
So there's the first part. And now I'm going to multiply by 1 liter per 1,000 milliliters. Then I'm going to multiply by this. Now, what am I going to put where? I'm going to make sure the liter goes on the bottom to cancel that. And the 0.15 goes on top. Then I'm going to multiply by 90.04 grams on top and 1 mole on the bottom. Okay, now I'm going to estimate my answer. 90 goes into 1,000 about 11 times. 11 goes into 250 about 25 times, but maybe like 24 or 23. 23 times 0.15 is going to be something like this. 25 times 0.1 is 2.5. 25 times 0.2 is 5. Let's see, 25 times 0.1 is, or I said 23. 23 times 0.1 is 2.3. 23 times 0.2 is 4.6. So the answer's got to be somewhere in the middle of a 2.3 and 4.6. So I'm going to say, I don't know, 3.5. So that's my ish. Turn on my calculator. 250 times 0.15 times 90.04 divided by 1,000. And I get 3.376. With 3 significant figures, it's 3.38 grams of C2, H2C2O4. So what was my ish? I forget. 35, 3.5?
Yeah.
So not too bad. So this is the type of work I would expect to see for a problem like this. At this point in time, I'm not really asking you to show me how to get the molar mass. You just better get it right. Any questions on this?
Nope.
Okay, we're going to move on.
No questions.
You do. Go ahead.
No questions, no.
Oh, no questions. I thought you said I have questions. I'm sorry.
Oh, I have a question, but it's about something different about the lab.
Well, why don't you go ahead and ask it? We'll take a little break from this stuff.
Be right back. Getting coffee.
Yeah, so basically, I don't think my dye works. I think it's tarnished. So I've just been kind of doing the lab without properly being able to see the amount of drops. So
Does your dye have some like bits in it?
yeah, is it a common thing? I can show you.
It can be a common thing. Let me ask you this though.
Can you see it on the screen?
Oh yeah, your dye looks horrible. It did not stay blue at all, did it?
Yeah. So is that a common thing?
It didn't happen to me. Hang on
I
a
had
second.
a problem though too.
Sorry, I'm still wearing my glasses.
Hang on a second here. Hold that up.
I don't want to take them off because then you're probably gonna see a crease around my face.
That doesn't matter. whenever I close my eyes, I see creases around your face.
But yeah, this is how it looks like.
Is that what yours looks like too, Charlotte?
No, mine's still kind of purpley, bluish.
Why don't you hold yours up?
Let me go.
I don't have any more dye. I used all mine up. Mine stayed blue.
Yeah, I was wondering if that's something I can buy at the store, or should I just kind of like pretend and just use that, see that as part of like an issue with my lab and just write it up that way?
Well, you didn't see any color change, did you?
No, not on anything, because it's just everything just became little bits of.
I'll tell you what to do. Charlotte, speak. Speak so that you're on the middle of the screen.
Okay.
That's not working.
No. I mean, mine's like almost all gone, so you can't really tell when I was talking about it, but it's very like flaky
Oh, yours did
and
stay pretty purple. So you had a little bit of color change. Is that right?
very slight,
It turned kind of pinkish when it was done, right?
very, very slight.
Yeah, then that's all you need. Now, let me ask you this, Charlotte. How many drops per 1 milliliter? You don't need that now that I remember. How many drops of dye did it take to change about your 0.2 grams of no, wait,
The 2 milliliter DVC solution or the diluted juice?
yeah, about how many drops did it take to change your diluted vitamin C solution?
Well, I don't think it's accurate, but I have 7 drops.
7
Right.
drops.
So
Okay.
when you did the lab, it was 8 drops. I did see the lab for the DVC solution, but the ratio I can't get at all is the diluted juice.
And how many drops did it take to change the diluted juice, Charlotte?
9.
9.
I
Okay.
still don't.
It's like I just came up with the number.
Yeah. Usually it's a ratio of 2 to 1. So when I I did the lab again for someone in the evening, and I kind of hid everything.
Yeah, I watched that.
But I think it took about 10 drops for the diluted vitamin C solution. And it took about 5 drops for the,
For 2 milliliters.
yeah. And it took
Of
about 5
diluted
drops
juice.
of the diluted juice solution.
Oh, okay. Because I watched the morning lab.
Yeah, in the afternoon it was more like in the afternoon lab, I think it was a ratio of like 8 to 5 or something like that.
Oh, okay.
But you probably didn't see how many drops it took to do the diluted juice solution because I kind of hid it, right?
Yeah, in the morning one.
Yeah, I
Yeah.
did it in the evening too.
Okay, so the
So
evening one does give you
the
the
important
ratio.
thing is that you be able to make these calculations. So what you want to do is use 10 drops for the diluted vitamin C solution
Uh-huh.
and use 5 drops for the diluted juice solution.
Okay.
And for the volumes of the diluted juice solution and the volume of the diluted vitamin C solution, just use 95.0. Fair enough?
Yeah, because I have my own amounts that I came up with, but since they're kind of irrelevant at this point, since I can't do the rest of it, you said to just do
0.
95.0, and
Yeah.
this is for both the diluted for the VC solution and also for the juice solution.
Right. And you're going to assume that you made them as per instructions. That is to say that when you made your vitamin C solution, you dissolved what was that? 0.25 grams in 50 milliliters or something like that.
Yeah.
And then you took 1 milliliter of that, right?
Right.
And you diluted that to, now we're going to say 95.0 milliliters.
Okay. Sounds good.
And
And
for the
then,
juice solution, we're going to assume that you took 2 milliliters of that, right?
yeah.
Diluted that to 95.0,
Mm-hmm.
and you were titrating one milliliter samples, I believe, or is it 2 milliliter?
2 milliliter. Yeah.
Okay, and you're titrating 2 milliliter samples. So
Okay.
we're going to assume that you took 2 milliliters of juice and diluted it to 95.0,
Okay.
and work with those numbers. Okay.
Okay. And I'll just take pictures of what I have, I guess, because
Yeah. Yeah. And we found out that for the file uploads, they need to be JPEGs.
okay. All right, we'll do that. So I'll just I just kind of crashed your Zoom. I was like in the middle of it and I was like, I can't do this. It's not gonna work.
Well, Charlotte probably appreciates the idea that she got close to the correct number of drops that we expect.
So I'm glad this was a common issue. It wasn't just me. So
Yeah. Mine
for
actually,
everybody that's gonna be doing their lab later.
I don't know how many people have an issue where the dye basically decomposed. It's more, usually it happens more like with what Charlotte has, where it's slightly colored. I mean, it's definitely a blue color,
Yeah.
but there's bits in it. And yours looks like bits
Yeah.
with stuff, with gray stuff.
This
Yours
one
looks
was just
like really bad
completely
copy.
done. Yeah.
Okay.
As soon as I opened it, I was like, this doesn't seem right, but I kept going and I was like, okay, let's just try, but yeah, it didn't work. Okay.
Uh,
Well,
so
I'll stay here and
after today's session, I'll post a little something for people who had trouble.
yeah, okay, perfect. So I'll just stay here and
Oh, okay.
sorry to crash your
No worries. So I'm going to change my share back here. And we're going to take a look at this next problem. If 50 milliliters of 0.025 molar copper 2 sulfate is diluted to 10.0 milliliters with pure water, what is the molar concentration of copper 2 sulfate in the diluted solution? Okay, so the idea behind doing this is pretty simple, but profound. So here's what I mean by simple but profound. If we take a look at our 4.00 milliliters of solution, 0.250 molar, we can actually calculate the amount of solute in there because we can do a C times V equals amount. And if we do that, we get 0.250 moles of copper 2 sulfate per 1 liter of solution. I'm just going to write solution since this whole problem refers to copper 2 sulfate. Times 4 milliliters. So I'm going to put times 1 liter of solution per 1,000 milliliters of solution, so that I can multiply this by 4 milliliters of solution. And we're going to end up with moles of copper 2 sulfate. And you can see that the number is going to be very small. 4 times 0.25 is 1. 1 divided by 1,000 is 1.00 times 10 to the minus 3 moles of copper 2 sulfate. So that's how much is in here. 1.00 times 10 to the minus 3 moles of copper 2 sulfate. Now, when you add 10 mils of H2O.
Hey, Tony.
Yeah.
Okay, so that first one you did was to figure out the concentration of the 4 milliliters. So then now we're going to figure out the diluted.
Not the concentration, the amount.
Okay.
So this was a CV equals amount. We were calculating the amount.
The amount. Okay.
Yeah, here's the C, here's the V, and here's the amount.
Okay.
So here, if we add water and we get 14.0 milliliters because we add these two numbers together. The amount of copper 2 sulfate will still be 1.00 times 10 to the minus 3 moles. And the reason that hasn't changed is because we didn't take any out and we did not put any in. We just put water in. So here, if C1V1 equals amount, and here if C2V2 equals amount, that means C1V1 equals C2V2. So what's really nice about this formula is the following. Here, we're solving for the molar concentration of copper 2 sulfate, so that's C2. So there's the formula for C2 on one side of the equation and everything else on the other. And do you remember all of the conversions we had to do for all of this? Well, this is what's nice about this particular problem. I can take my C1 here. I can take my V1 here. I can take my V2, which is 14.0 milliliters, not 10. Oh, actually, it is 10. I thought it was adding 10, but it's not adding 10. It's to a final volume of 10, which means I have to go back here and change this to 10. And actually, this does look more like 10 than 14 the way I've drawn it. Okay, so going back to here, the milliliters cancel. And what are we left for units? We're left with molar copper sulfate. Okay, so 0.25 times 4 is 0.1. 0.1 divided by 10 is 0.01, I believe. And how many significant figures do we get? We get 3 significant figures. Here, I've only shown 1 significant figure, so I have to put 2 zeros here. And this would be a perfect example of how to show this problem. Any questions about this one?
Yeah, I do.
Go ahead.
So I liked when you taught us how we basically just laid out, okay, what C1 is, what V1 is based off the problem. And
Yep.
then
So we can do that. C1 is equal to 0.0250 molar copper 2 sulfate. V1 is 4.00 milliliters. V2 is 10.0 milliliters, and C2 is what we want.
then yeah. Then we just plug it all in like you did.
Yeah, plug it all in.
Okay.
And this is not a bad way to start making the list, but I often don't show the list in Chem 1A because you guys have already done chemistry before. And it's easier for you than a novice to say, oh, that's C1 and plug it in there. Was that your question there though, Charlotte?
Yeah. Okay.
Yeah, so making the list helps, and you should do that if it's going to help you to solve the problem. Kind of like opening your eyes when you're driving a car usually helps. So, but I think opening your eyes when you're driving a car is more imperative than making the list here. Okay, which of the following methods would you use to prepare 300 milliliters of 0.500 molar potassium dichromate? Okay, so this says add 30 milliliters of 0.150 molar potassium dichromate to 270 milliliters of water. And this says dilute 250 milliliters of 0.600 molar potassium dichromate to a volume of 300. So let's take a look and see what concentrations we would get both ways, okay? So here for A, what is C1? C1 is going to be 1.50 molar. And I'm going to leave this off because we're talking about potassium dichromate for this whole problem. V1 is going to be 30 milliliters. V2 should be 300 milliliters, right? Because we had 270 plus 30.
Yeah.
And C2 is the question. So C2 is C1 V1 over V2, which is 1.50 molar times 30 over 300. And when we do this problem, we get 0.15 molar, right? Or excuse me.
15? No.
Well, I think we get 0.15.
What am I thinking of?
We get 0.15 molar solution. Now for B, C1 is going to be 0.600 molar. V1 is going to be 250 milliliters. V2 is going to be 300 milliliters. And C2 is what we want. And remember, I'm going to show you the problem again. We want to get a 0.500 molar solution. So in this case, we get C2 is equal to 0.600 molar times 250 milliliters over 300 milliliters. And let's see what we get here. Now, 6 will go into itself one time, 6 will go into 300 5 times, right? But really that's not 5. I guess that is 500 milliliters. And then 250 over 500 is 0.5. So here I get 0.500 molar solution. So I'm going to have to go with B for my diluting because I get the right concentration. Now, could we take this method and make our solution? And the answer is absolutely. But clearly, this is too dilute. So you either want to use more of this stuff, and it's probably more like 100. All right. Any questions about this one?
No.
Okay, so we're going to move on. A saturated solution of milk of magnesia has a pH of 10.5. What is the hydronium ion concentration in this solution? And is the solution acidic or basic? So I'm going to teach you two formulas you should memorize that deal with pH. One is as follows. The hydronium ion concentration is equal to 10 to the negative pH. Another way to write this is H plus is equal to 10 to the negative pH, because a lot of the times we think of H plus as being the same as H3O plus. Okay, so that's one formula. The other formula is the following, that the pH is equal to negative log of the hydronium ion concentration, or pH is negative log of H plus. These mean the same thing. This concentration is molarity. So it's got to be a molarity concentration. So when they ask for the hydronium ion concentration of the solution, they're looking for a molarity. All right. Now, the other thing that we need to know is the pH scale. And you need to memorize this. On the pH scale, 7 is what's considered to be neutral. And that's because the proton concentration is equal to the hydroxide ion concentration. Anything less than 7, so 1, 2, 7, but less than 7, so I'm going to say 0, greater than 0, but less than 7. That means the hydronium ion concentration is greater than the hydroxide ion concentration, so it's called acidic. Now, when the pH is greater than 7, well, we'll say less than 14, there's really no limit here, to be honest. This means that the hydronium ion concentration is less than the hydroxide ion concentration. And we know hydroxide is our base. So when you have more base than acid, it's basic. So you need to memorize all of this stuff for this type of problem. Or maybe you put it on your note card, which you guys are working on, right? Okay. So here, if we want to get the concentration of the hydronium ion, it's going to be 10 to the negative pH. So that's going to be 10 to the negative 10.5. And this answer is going to be molarity. Okay, so I'm going to go ahead and put a molarity there. Now on my calculator, this is how I do it. Turn on your calculator. 10 caret negative 10.5. And I get 3.16 times 10 to the minus 11 molarity.
Oh, it's acidic.
And actually, I believe this should be 3.162 times 10 to the minus 11 molarity. Here we have 3 digits. And here we have 3 significant figures, and that's how you match them.
Oh, yeah. It's the amount after the decimal.
Yeah, the number of digits after the decimal in the concentration equals the number of significant figures in the pH.
And that's only for rounding with log.
Yeah, this is logarithms. So this is for using logarithms. So this is what we would expect to see for your answer, something like that. I would also like to see this. So the formula, you using the formula, then the answer. Do not leave your answer as 10 to the minus 10.5. That's wrong. Now, is the solution acidic or basic? Well, the pH is 10.5. 10.5 is greater than 7, so it's basic. So if we look at a number scale, this is going to be basic. This is going to be neutral. And this is acidic. And I mean that anything smaller than 7 is acidic, technically. So 6.9 is acidic, although it's really close to neutral. 7.1 is basic, although it's really close to neutral. Any questions about the pH scale and those calculations? Okay, let's take a look at another one. What is the hydronium ion concentration of a 1.2 times 10 minus 4 molar solution of HCl4? This is hydrogen, or actually this is perchloric acid. It's a strong acid. So that means that the perchloric acid does this and so if we begin with 10 of these and 0 of these and 0 of these, you will end with 0 of these, 10 of these, and 10 of these. Okay? The important thing here is that if you look at how much H plus you end up with, it's the same as the acid that you started with. So we would say that the acid concentration is equal to the H plus concentration for a strong acid. So when they ask us what is the hydronium ion concentration here, we would say that the hydronium ion concentration, which is the same as our H plus concentration, is the same as our acid concentration, which is 1.2 times 10 to the minus 4 molar. And this is due to the strong acid. So they're the same because this is a strong acid. So what is the pH? The pH is negative log of H plus, which in this case would be negative log of 1.2 times 10 to the minus 4 molar, but we're not going to put the molar in there. And then here's what we get. For this calculator, let's see how we do this. I believe I pushed negative log. Where's my log button? There's my log button. 1.2 second EE negative 4. And I usually don't push the second bar. I just put equal. And I get 3.9204. Now here we have two significant figures, right?
Mhm.
Or actually we have one digit after this number. So this ends up being like 4. pH is 4. Okay, so that's how you do this problem. This is the work I'd expect to see. I was going to say, wow, this looks like one we just did. Okay, make the following conversions. This is just practice for you using those formulas. So I'm going to skip this one. What mass in grams is required for complete reaction of 50 milliliters of 0.125 molar HNO3? So this is a good problem for us to finish off on. So this is a stoichiometry problem. Now with stoichiometry, we're used to going from grams to moles to moles to grams. Here we're going to do something different. We're going to start off with 50.0 milliliters of this solution and a 0.125 molar concentration. We're going to use this to get the moles of HNO3. Now they ask for what mass in grams. We're going to use this to get the moles of Na2CO3, and we're going to use this to get the grams of Na2CO3. So here in this column, we're talking only about our moles of HNO3. And in this column, we're talking about sodium carbonate. And you can see that for me to go from this column to this column, I have to use the mole to mole conversion. So now we know this molarity is moles per liter, and this is milliliters. So I'm going to take my 50 milliliters, convert that to liters. Then I'm going to use the molarity, convert that to moles. Then I'm going to use my balanced reaction and get the moles of sodium carbonate. And then I'm going to use the molar mass of sodium carbonate to get the grams of sodium carbonate. So you can see that this last arrow is this one here, this arrow is this one, this arrow is this one, and this arrow is an extra one for me to get to liters so I can use molarity here. So let's see how this all looks together. So 50 milliliters of HNO3. This is solution, but I'm not going to write the word solution down. Times 1 liter of HNO3 for 1,000 milliliters of HNO3 times here the 0.125 would be 1 liter of HNO3 and 0.125 moles of HNO3. And you'll notice I did not write this out as follows before doing this, because I've gotten a little bit comfortable knowing what that means. So I went from here to here directly. But, you know, if you're still not comfortable with what this means, then by all means, write it out. It's not cheating. And then here, I'm going to write 2 mole of HNO3 to 1 mole of sodium carbonate. And you might be wondering, where does he get those numbers from? And the answer is from this balanced reaction right here, 2 moles of HNO3 to 1 mole of sodium carbonate. And then we need the molar mass of sodium carbonate, which is 22.99 plus 22.99 plus 12.01 plus 48.00. You can see that this really is close to, what is that, 106. Really close. Not quite. So 105.99 grams per 1 mole. And all of this should get us the mass. And when we estimate the answer, 105 goes into 1,000 10 times. 10 goes into 55 times. 5 times 0.125 is, well, 0.125 is like 1/8. So 5 times 1/8 gives us like, I want to say 0.7. So 0.7 divided by 2 is like a 0.35. I don't know if I estimated correctly, but we'll find out. So 50 times 0.125 times 105.99 divided by 1,000 and divided by 2. And I get 0.33. So that's how you do a problem like that. Now, I think you can see, if I lower this a little bit, that this little roadmap helps out a lot with figuring out what to do here. So you kind of want to get used to making these little roadmaps. And you can see that this roadmap here, I took it and put it down here and kind of stretched it out. And it takes that, I think it takes that sort of preparation to be able to do a problem like this, because coming up with this without doing the rest of the work is very difficult to do. Any questions here? Okay. Thank you for tuning in. Appreciate it. Hopefully I'll see you guys tomorrow. I don't know if I'm going to be able to Zoom tomorrow or not. I may be incapacitated.
Oh,
Yeah, I'm supposed to get my first shot today.
oh.
Okay. My dad just got his 2 weeks ago.
Oh, great.
Yeah, the
How-
Pfizer one.
Yeah, I'm getting the Pfizer one, it turns out. How's your dad?
Yeah. He's got both of them already, and he hasn't said anything about feeling any type of way at all. So
Well, that's great.
I
That's
got
great.
both of them, but I got the Moderna.
yeah, my dad's 67, I think. He's 67. But yeah, he hasn't reported anything at all. And he's the type of person that will say something if he's not
Oh,
feeling good.
he will let you know he's not feeling well, huh?
Yeah.
For me, I'm getting mine because they're doing that part of the tier where they're doing educators.
That's
Okay.
good.
So I got the chance to do one today, so I'm going to go ahead and take it.
Yeah,
You probably
that's
feel
good.
fine after the first one. It's a lot of people who don't feel very good after the second.
Yeah, but you know what? If I don't feel well, I don't want to Zoom. And you know what? Maybe I do feel well, but I still don't.
Okay.
It's
I'm gonna,
okay if you need a break.
I'm gonna have to go. Oh, geez, it hurts. And I'm gonna, of course, get it in my right because I write with my left. So there we go.
Yeah.
I'm kind of excited to finally get on that bandwagon.
Yeah.
So Charlotte, you must be a healthcare worker of some sort.
Yeah, I've given a ton of the vaccine.
So that's why you have yours.
It's fun.
You've already gotten both or just the first one?
Yeah, I've gotten both.
Okay.
Yeah, for you younger people, you're just gonna have to wait
Work in healthcare.
or get a job as a LVN or something,
I know.
or a EMT or a paramedic.
Yeah.
Boom, you're gonna go to the front of the line. Actually, what I've heard is that if you skip your time to go, you can go at a later time, but you're not going to go to the front of the line just because you skipped your time. So, and I have the feeling that as they work down the age groups, there are more and more people in those age groups. So it's going to move from age group to age group more slowly
True.
because there's more people to vaccinate.
Yeah. I also think
Plus,
they're coming out with more vaccines, so hopefully that kind of
yeah, the Johnson sounds like a great one. You just take one shot, one and done.
yeah, that would be great.
Yeah.
It's been interesting trying to coordinate to get people to come back in for their second one. It'd be a
Really?
lot it'd be a lot easier if we could just do the one shot.
Yeah. Well, and then isn't there like different times? Like it's 3 weeks for the Pfizer and 4 for the Moderna, or vice versa.
Yeah, that's correct.
Yeah. And then, from what I understand, though, the CDC has decided everyone should get at least one as quickly as possible before you get your second. So your second may be delayed, from what I understand.
Mm.
Yeah. For my dad, he got both of his appointments at the same, I mean, he got them scheduled at the same time. I scheduled it for him in but he's in SoCal.
Okay. Great.
Yeah.
All right. Well, I thank you guys for calling in and keeping me on my toes about different things. And I will post an announcement about the vitamin C lab. Two of them, one where you want to submit your files as JPEGs, and the other one that you want to, if your dye has turned, you're going to submit a photo of your turned dye and go from there. Charlotte, I think the numbers that you got are perfectly fine, and I would use them. Okay.
I hope so because I'm done and I'm going to work later.
Have you already calculated the answer?
Yeah, and it's not anywhere close to the milligrams of vitamin C on my container.
Well, what did your container state and what did you get?
9 milligrams was the given.
9?
Mhm.
9 milligrams per
Mhm.
serving?
Yeah,
There's not much vitamin C in that stuff.
right.
Yeah. And with your numbers, you probably got more like 150,
I got like 300.
300. Yeah. Well, that's what you're going to go with.
Okay.
At least you got something to write up in your discussion, don't you?
That's what I wrote about, yeah.
Yeah. You can write about, well, the dye didn't seem to be very stable. So it was difficult to tell the color change. And one of the things that you should think about though, Charlotte, is this, that the answer came out to be milligrams, didn't it?
Mhm.
You didn't get that there were grams of vitamin C in there or micrograms of vitamin C. It came out to be milligrams, and it was supposed to be milligrams, right?
Yeah, I converted.
So if you think about it in that sense, that when you're, say, how do I say this? When you're trying to hit a target, it's nice to know that you're in the ballpark and that you're not throwing the ball in the wrong direction. And so the fact that you're getting milligrams means that you're throwing the ball in the correct direction. Does that make any sense?
Yeah.
Okay. All right. Well, have a good day, you guys. Maybe I'll see you at 1:15 if you call in.
Okay.
All right, have a good one. Bye.
Bye-bye.